Hello online learners. Welcome to Lesson BC Online YouTube channel. Today the online teacher will explain about electric field concept, electric field lines and electric potential, voltage. Stay tuned.
Welcome back to The Explainer. Today we're diving into something you can't see but that shapes basically everything, from the tiniest atoms to entire galaxies. We're talking about the electric field. We're going to look at what it is, how we can actually map it out, and how it stores energy. So let's jump right in. First things first, let's tackle a question that really puzzled the early scientists. So picture this. You've got two electric charges just sitting in empty space. How on earth does one know the other one is there? How does that force travel across a total vacuum? Well, it's not magic, but it is one of the most important ideas in all of physics. The answer, it turns out, is that charges don't actually interact with each other directly over a distance. Nope. Instead, every single charge creates this invisible influence that fills all the space around it, and we call this a field. Okay, so here's the big idea. A charge literally changes the space around it, creating what we call an electric field. Then, when you put a second charge into that space, it's the field right at that spot that does the pushing or pulling. The field is the middleman. It's a real physical thing that's now a property of space itself.
And this field isn't just some abstract concept. We can actually calculate its strength. This formula right here tells us that the field strength, that's E, depends on the charge creating it, Q, and how far away you are, R. Now that R squared on the bottom, that's a huge deal. It's what we call an inverse square law, which is just a fancy way of saying the field gets weaker and it gets weaker fast as you move away.
This image really helps us picture what's going on. These arrows are what we call field lines, and they show the direction a tiny, imaginary, positive charge would get pushed. So because the charge in the middle here is positive, all the field lines point straight out, away from it. Now, this leads to a really useful trick. For something like a perfectly charged sphere, the electric field outside of it looks exactly the same as the field from a single point charge located right at the center. It's a great little shortcut that makes the math for big, complicated objects way simpler. So if this field is an invisible property of space, how in the world do we get a feel for its shape and its strength? How do you even begin to draw a map of something you can't see? Well, to map the field, we use those electric field lines we just talked about. And they follow a few simple rules. They always point away from positive charges and towards negative ones. Where the lines are packed close together, the field is strong. Where they're spread out, it's weak. And this last one is absolutely crucial. They can never, ever cross. I mean, think about it. If they did, the force at that point would have to point in two directions at once, which is just impossible. All right, let's compare two different scenarios. On the left, you've got that radial field from a single point charge we've seen. But look at the right. Here, we have a big, flat sheet of charge. And what it creates is a totally uniform electric field, where all the field lines are parallel and the force is exactly the same everywhere. Pretty cool, right? Now check out this more complex pattern. This is the field you get from what's called an electric dipole. That's just a positive charge and a negative charge near each other. You can see how the field lines trace these beautiful, elegant curves. That's the exact path a positive test charge would take as it gets pushed away from the positive and pulled in by the negative. Okay, so we have a map of the field's force, but there's another just as important way to look at all of this, and that's through the lens of energy. You know, the best way to get your head around this is with an analogy. I want you to think of a positive charge as creating a big electric hill. If you put another positive charge nearby, it's going to want to roll down that hill, right? Away from the first one. The height on that hill is like its potential energy. And a negative charge? Well, that creates an electric valley that positive charges just want to fall into. In physics, we have a name for this electrical height. We call it electric potential, and we use the letter V. It's basically the amount of potential energy a charge would have at a certain spot divided by the size of the charge itself. What's cool about this is it gives us a value for the energy of a location, no matter what kind of charge we put there. And this brings us to a unit you've definitely heard of, the volt. But a volt isn't some mystical thing on its own. It's just a shortcut for saying joules per coulomb. So when you see a 9-volt battery, what that really means is that it gives 9 joules of energy to every single coulomb of charge that passes through it. So a volt is just a measure of energy per charge. Let's go back to our map analogy for a second. You know how a topographical map has contour lines that connect all the points with the same altitude? Well, an electric field has something similar, called equipotential surfaces. They connect all the points with the same electric potential. For a single point charge, these are just a series of perfect spheres. You could move a charge anywhere you want along the surface of one of these spheres, and it wouldn't take any work at all. It's just like walking on perfectly level ground. All right, we've thrown two big related ideas at you, the electric field and electric potential. So let's put them side by side and just quickly summarize the key differences so it all sticks. So the electric field is a vector. That means it's got both strength and direction, and it tells you about the force a charge is going to feel. Electric potential, on the other hand, is a scalar. It just has a magnitude, a number, and it tells you about the potential energy at that point. So to use our analogy one last time, the electric field is how steep the hill is, while the potential is how high the hill is. Two different ways of describing the same landscape.
So we've seen how to describe the field for simple things, like a point or a sphere. But what happens when you have more complex arrangements of charges? Is there some kind of powerful shortcut to figure out the field without all the hassle? Well, the answer is a huge yes, and it unlocks a much, much deeper understanding of how electricity and magnetism really work.
That is all about today's lesson. If you have any questions, write on the comments section and the online teacher will reply to you. Do not forget like and subscribe our Physics and ICT YouTube channel. Thank you online teacher, thank you online students. See you in another lesson. Until then, goodbye everyone.